This is video 1,436,923 dealing with Maths Methods 3 and 4 revision. This particular video, Chapter 6 on circular functions, a particular chapter very dear to my heart. As I'm pretty sure you already know by now, these questions and examples in the video are taken from the Cambridge Essential Mathematical Methods 3 and 4 CAS textbook. No intention has been made to infringe copyright, and my apologies if it has. However, it is simply a video resource for my current students to assist in their preparations for their VCE examination. Thank you so much for your understanding. Okay, so let's do a little bit of prerequisite learning, and it takes about 4.5 seconds, and it's something that's just a recap from methods 1 and 2, and that is, if you think of a circle, then how many degrees are in a circle? There are 360 degrees in a circle, but there are also such things as radians, and we define that 360 degrees is the same as 2 pi radians, which would suggest that 180 degrees is equal to pi radians, and a radian is actually given by this little c above, and so 1 degree is equal to pi divided by 180 radians, or 1 radian is equal to 180 over pi degrees. Right, so there's the prerequisites, nothing particularly exciting in that, but this unit circle is, I have to say, probably one of the smartest things you can possibly come up with. So I'm going to deal quite a lot with an actual picture of the unit circle, and let's do that now. So here is my unit circle, right? It's a circle whereby the distance along this line here from the origin, so let's call that 0, through to this point P, which has a coordinate a comma b, is equal to 1 unit, right? So that's why it's called the unit circle. Now I haven't put anything on here at this moment in time, and I'm not going to put x's and y's, and you'll see why shortly. This angle here we're going to define to have some size of theta, and so, well, using a bit of trig, a bit of excitement and what have you, then I can make some pretty stunning definitions, and by that I mean to say I know that this length across here is actually cosine theta, right? So the length of this line is equal to cosine theta. Why? Because that's equal to 1. And if you use SOHCAHTOA, you can pretty much prove that, you know, this length here and that length related is, you know, cosine theta. In the same way, we know that this height is equal to sine theta, right? Now that's going to become critically important at this moment in time, because what we're going to start doing is thinking of horizontal distances and vertical distances in terms of sine and cosine. Now this is a positive x direction and positive y direction, so sine and cosine, that's positive cosine, that's positive sine. And because we have this unit circle, you can label things around the edges in terms of either degrees, or you can turn it in terms of radians. And at this moment in time, I'm going to say, well, that's 0. Now we tend to label this turning around anti-clockwise. This becomes pi on 2 radians, which you hopefully will agree is 90 degrees. This is pi radians, 180 degrees, 3 pi on 2, and back to 2 pi. Right? And this situation here is 0 and 2 pi actually is used as a bit of a trick later. So just remember. So let's do a trivial and rather pointless example. We'll come back to the idea that, well, what if I wanted to find the sine of pi? Well, if you think of the sine of pi, here is pi, right? So the sine of pi, which means I'm going to have a line extending from this point here along here. Right, so that's going to be my line. Now you'll notice I don't have any triangle here, right? I can't have a triangle because it's just one line. So as this has no height, basically the sine of pi is equal to 0. Why? Because exactly as I've just said, there is no height, there is no vertical distance for the sine of pi. How can we relate that to another example? What if I wanted to find the sine then of pi on 2? Well, if we draw our line of pi on 2, that will be this vertical line here. And what do we find? Well, there would be no cosine value because the cosine of that would be 0. But what we notice is it's this vertical line. It stretches all the way from the bottom to the top. And I know the length of this part of my circle is 1, so the sine of pi on 2 is 1. And likewise, you can work out the cosine of 0, for example. What is the cosine of 0? Well, the cosine of 0 is this line here, right? So we're drawing a line from all the way across, and, well, cosine of 0 becomes equal to 1. So using this unit circle becomes quite fascinating, if not incredibly funky. and it's going to build the basis of where we're going to move to now. So let's go back to a clean example, and once again we're going to label this part here theta, and we know, because we've just decided that, this is cosine theta and this is sine theta. So looking at this point AB, what I know is that we have a coordinate position of x and y. So our standard coordinate position of x, y is actually just going to be called A and B. So right, for this point here, what do I know? Well, I know that sine theta is going to be equal to, well, sine theta is my vertical distance is b, sine theta is b. What is cosine theta? Well, cosine theta is my horizontal distance, and by this coordinate position my horizontal distance is a, and we know that tan theta, which is exactly the same as sine theta, divided by cos theta, would be equal to b upon a. Now those definitions come in incredibly important, right? And if ever you're stuck or confused, I would always suggest using first principles now to go from this idea. Well, how does that help us? Well, let's go back. This is 0, this was pi on 2, this is pi, 3 pi on 2, and obviously we go back to 2 pi again. So what if we were being asked to find, I don't know, the sine of pi minus theta? The sine of pi minus theta. Well, what I'm going to do first is I'm going to draw a line. I'm going to draw a line here. Why? Because here is pi, and if I'm taking theta away, then it's going to be here. This is pi minus theta, which suggests that this angle here is theta. Now, something to note, or a revision, remember we always work anti-clockwise around our circle. So this is pi minus theta because this value here, I'm not quite at pi because I've got theta to go. Right, okay, so let's look at things in terms of lengths. Well, bearing in mind this is theta and this is theta, I now know that this length here has got to be exactly the same as this length here. Well, this length here was equal to a, so I'm going to tell you now that that becomes equal to minus a. Why is it minus a? Because if this is a in a positive direction, this must be a in a negative direction. What is this vertical height? It's b in the positive direction. This height here is b in the positive direction. This just becomes b. Well, I now actually have all of the information I need to be able to work out our sine of pi minus theta. Well, remember, the sine is the vertical height. So the sine of pi minus theta is equal to b. And the cosine of pi minus theta is equal to negative a. And the tan of pi minus theta is equal to b over negative a. Why? Because tan is sine over cos. But hold on a moment, we already have some information here that tells us, well, b is the same as sine theta. So that is exactly the same as the sine of theta. Well, what's negative a? Well, if a is equal to the cosine of theta, then negative a must be equal to the negative cosine of theta. And if tan is b over a, then this must be equal to the negative tan of theta. And there we go. We've now come up with some identities that tell us that sine of pi minus theta is exactly the same as the actual angle. If I know that this angle here is 30 degrees, then I know that the sine of 30 degrees is exactly the same as the sine of pi minus 30 degrees. Well, pi is 180, minus 30 is 150, so there we go. What about the rest of the quadrants? What about this quadrant here and this quadrant here? Well, let's work it through very quickly. Once again, let's put our theta back on, and this is cosine theta, and this is sine theta. What if I now want to find the sine? So what happens if we want to find the sine of pi plus theta? Well, quick sketch. This is pi. So if I'm going to do pi plus theta, there we go, that's pi plus theta. So this point here is pi plus theta, because we're pi and we're adding on theta. Let's go back. We know that sine of theta vertically is our y, so that's equal to b. And we know that cosine in a positive direction is equal to a. So drawing our unit triangle, what do we get? We get, well, this must be minus a because it's going backwards on itself and it's going down, so it must be negative b. All right, okay, so where do we go? So the sine of pi plus theta, well, sine is our vertical distance, it's equal to negative b. And in the same way, we can find the cosine of pi plus theta is equal to, well, that's the horizontal distance, that's negative a, and therefore the tan of pi plus theta must be equal to minus b over minus a, which is equal to b over a. But hold on a moment, we already have from our previous slides the idea of we know that a, b and b over a, well they are, so if b is equal to sine theta, then that must be equal to the negative of sine theta, because b is sine theta, so minus b must be minus sine theta. Cos theta is a, so that must be equal to the negative of the cosine of theta. And tan, which is b over a, well, there we go, is exactly the same as tan theta. Same idea. Now what would that be? Well, let's see whether we can work out the sine of 2 pi minus theta. All right, the sine of 2 pi minus theta. Well, where's 2 pi? Well, 2 pi is here. And we know what theta is now. So this is theta again. This is cosine theta. This is sine theta. And just putting back on our values, this is going to be equal to a, and that's going to be equal to b. So if we're now going to do the sine of 2 pi minus theta, that's going to be here. And so there's my theta. Right, unit triangle, draw that quickly. What do we notice? Well, we notice the horizontal distance of this triangle is equal to a, and the vertical distance is equal to the negative of b. And so that seems to be pretty much all the information I need. So the sine of 2 pi minus theta, which is just the vertical distance, is equal to minus b. So what must the cosine of 2 pi minus theta be? Yep, fingers crossed, it's the horizontal distance, which is a, and in the positive direction. And the tan of 2 pi minus theta is equal to minus b over a. But we already know what each of these are because we've already worked it out before. We already know that sine theta is equal to b, and so that must be equal to the negative of sine theta. And a, we know, is cos theta, and that is equal to the negative of tan theta. What we tend to find out, and this is something I was taught at school, obviously, is that in this first quadrant, all of sine, cosine, and tan values are positive. In this quadrant, what we find is just the sine values. Here, the tan values are all positive, and here, the cosine values are positive. Now, I remember this as all stations to Canberra, but other people use it as cast, C-A-S-T, or cats, C-A-T-S, or I'm sure there's lots of other ways. In fact, I'm pretty sure that someone says that all students talk crap, but I won't possibly swear in my videos. So, how is this of use to me? Well, as I say, if I'm given that the sine of theta is equal to 0.5, and I'm told that the cos of alpha is equal to 0.6, how would I find the values of sine of pi minus theta? Well, sine of pi minus theta. There is pi minus theta, puts it in here. So what I already know is that's exactly the same as the sine of theta. Why? Because we've got the screen from before, you can go back in the video, and you all have proven that the sine of pi minus theta is exactly the same as sine of theta. So in which case, the sine of pi minus theta is equal to 0.5. Why? Because the question already told us that the sine of theta was equal to 0.5. Ooh, this is exciting. And what about if I wanted to find the cosine of 2 pi minus alpha? Well, 2 pi minus alpha is down here. We've decided that's exactly the same as cosine of alpha, so that will also be equal to 0.6. Why? Because they've told us the cosine of alpha is 0.6. Now, some people get confused with these thetas and alphas and what have you, but it's just they're the Greek letters. They're used to stand for values of, so you see, I could have called that alpha, all right? Don't get phased, just look at the general idea of the unit circle. And just as I said, we'll do a quick example of what they call complementary relationships, all right? And that is the case of, let's say we had we'll go back to this example here, where what we're trying to find out is pi on 2 plus theta. All right, we'll do pi on 2 plus theta. Right, now normally we have our triangle coming off the horizontal axis, and that's quite important to us with the unit circle. It makes life a lot easier, but maths isn't always about being easier. Now please imagine that this triangle is the same size as this triangle here. So here we go. So let's draw my triangle in. I know that that distance there is theta, so I now know that this distance here is also theta. Horizontally, that is A, and vertically, it's B. Now, because it's the same triangle, that must mean that this distance here is B, and it must mean that this distance here is, and this vertical distance is A. But we know from our unit circle that vertical distances are equal to sine theta. So we know that the sine of pi on 2 plus theta must be equal to, sine is this vertical distance, is equal to A, and we would know that the cosine of pi on 2 plus theta would be equal to negative B, and we would find that the tan of pi on 2 plus theta would be equal to A over negative B. But how does that help? Well, we know that A is cos theta. We've already known that. We've known that from the beginning, that A is equal to cos theta. So this must be exactly the same as the cosine of theta. And in the same way, because B is equal to the sine of theta, that must be equal to the negative sine of theta, and that must be equal to the negative tan of theta, right? So we can build up our complementary relationships simply by using exactly the same idea and making sure that our triangle, our unit triangle, has the right values of A and B written on it, right? So again, each of the quadrants, that one and that one, all have their own complementary relationships. Now, you can go and prove them on your own time, or you can just copy them out and stick them into your notebook. But either way, using this unit circle will save a lot of time. Something else that comes in quite handy in circular functions is the idea of trig identities, or rather exact values for circular functions. So if I asked you to find the sine of 30 degrees, you would probably jump for your calculator and it would come out with 0.5. Right? But what if you wanted to find the sine of 45 degrees? Right? Well, without absolutely knowing all your exact values off the top of your head, you may dive for your calculator and it may in fact give you 0.707 and sadly when I was at school, yes, I had to remember all these things. Torture! Including the quadratic formula. Totally different argument. But the idea is there a quicker way of finding this out? Well, yes, there is. There's the two, what I will call triangles, right? Now, one of the triangles I'm going to give you straight away is probably one of the easiest ones. Now, they're based on the idea of Pythagoras. If this is 1 unit and that's 1 unit, then I know that this triangle must be 45 degrees. And what would that make the length of this? Well, 1 squared plus 1 squared is 2. And square root it gives us root 2. How does that help us? Well, let's think about it. What if I want to use this triangle now to find the sine of 45 degrees? What do I know sine is? Sine is opposite over hypotenuse. Opposite over hypotenuse is 1 over root 2. There you go, you've got your exact value. We'd probably want to rationalise the fraction, so it becomes root 2 over 2. What about the cosine of 45 degrees? Cosine is adjacent over hypotenuse, and what's that going to give you? Yep, again, 1 over root 2, easy peasy, which again is root 2 over 2. And what about the tan of 45 degrees? Well, you could do this fraction divided by that fraction. Well, that seems to work for me. But again, tan is opposite over adjacent, so it's 1 over 1. So the tan of 45 is simply 1. Right, so one simple triangle, 1, 1, 45, off you go. What's the other triangle? Just as easy, really. Same idea, it's a right angle triangle. There's my right angle. What we do is we have 60 degrees here. That becomes 30 degrees. Hopefully you're all aware why. And what we just remember is that this is 1 and that's a side length of 2. Right? Now, there is no way that I can tell you how to remember that because it's just something I've learned. But if we work out our side length here, we find out that becomes root 3. And so now I can find the sine of 30 degrees. How? Well, there's 30. Sine is opposite over hypotenuse. It's equal to half. Job done. What about the cosine of 60 degrees? Cosine of 60 degrees. Caught a herring. Oh, it's half. Ooh. What about the cosine of 30 degrees? Caught a herring, root 3 over 2. And what about the tan of 30? Trawling off America, 1 over root 3. Right? So these two triangles, 1 and 2, are really quite useful to help you finding exact values. Sine of 0? Well, you can use your unit circle for that. The sine of 0 would be equal to 0, right? We'll come back to the idea of trig graphs shortly as well. But in summary, you could put all of that in a table and learn the individual values, or you can just learn the two triangles and make life a lot easier for yourself. Now, what you may have noticed from the unit circle is that actually there's more than one value for sine, cosine, and tangent in the period of 0 to 360 degrees, all right? So there's more than one value. Here is 0, here is, I'm going to write it in degrees for this moment, 90, 180, and 270. And we'll go back to 360 as well. So what we notice is that if this angle here was 30 degrees, and we use our all stations to Canberra business, then what I see is in this quadrant here, sine is also positive, right? Sine is also positive. And this is where we start using the symmetry of this x-axis, because it becomes incredibly important to me, right? We've already worked out all the rules, but what we can actually do is you just draw a straight line here and mirror 30 degrees in that quadrant, because that's where sine is positive. You're looking for another angle where sine has the same value as it does in here, for example, 30 degrees. Well, if this is 180 and this is 30 less than 180, that must be 150 degrees. So I know that the sine of 30 is exactly the same as the sine of 150 degrees. Whoa. Right, but what about the cosine of 30? Well, let's go back. Here is my cosine. I draw a line down here of 30 degrees. And what do I notice? Well, it's come under the line, it's going the other way around. So you could start thinking about things as being minus 30 degrees, and we'll come back to that one later. Or 360 minus 30. So the cosine of 30 degrees is exactly the same as the cosine of 330 degrees. And what about the tan? What about the tan of 30 degrees? Well, if we think about it, where's tan? There we go, tan of 30 degrees. So we draw a line there, we do 30. 180 plus 30 is the same as 210. Well, there you go. This unit circle now allows me to find angles that are the same. So what was the sine of 30? What if I had to find the angles between 0 and 360 degrees where sine theta is equal to 0.5? Sine of theta equals 0.5. Well, we'd find the first angle. Let's go back. Well, we know from a previous screen that the first angle that has 0.5 as an answer is 30 degrees. So the first angle we'd write down is 30 degrees, but we now know using this information here there is another angle at 150 degrees, so my solution would be 30 degrees and 150 degrees. Quite a nifty, powerful little thing here. What about if I have the idea of trying to find the sine of theta is equal to minus a half? Minus a half. Well, that basically means minus a half. If I put that onto my calculator, I should get out minus 30 degrees. Well, what does minus 30 mean? It literally means if you're going this way around your unit circle and your values are positive, then going this way around means you're using minus values of sine theta. So let's see. So here's an angle here, right, of 30 degrees because we're coming the other way around. Where else is sine going to be negative? All right, we've got all stations to Canberra, right? So we now know because cos is the only thing in this quadrant that's positive, then sine is negative. Where else will sine be negative? Well, it's not going to be here because all of them are positive. It's not going to be here because all of the sine values are positive. It's got to be here. And in the same way, we just reflect and have this angle here as 30 degrees. Well, if this was 0 and 90 and 180 and 270 and 360, then we should be able to work out this angle here is 330 degrees because it's 30 less, and this angle here is going to be 180 plus, which is 210 degrees. And so my values work out to be theta is equal to 210 degrees and 330 degrees. Now this is assuming that they want solutions that fall between 0 and 360 degrees. But what if they wanted values to fall between, I don't know, let's say minus 180 and 180 degrees? What would we do? Well, we just use the idea that minus 180 and 180 means it wants values going in this half of the quadrant and this half of the quadrant. Well, the values of 210 and 330 don't make any sense to me whatsoever. So let's look at this one. Well, we already know that this angle here is minus 30, right? So one of the angles would be equal to minus 30 degrees because I've gone 30 degrees under. What about this? Well, how big is it from here all the way around to here? Well, it must be equal to 180 minus 30 degrees, so basically 150 degrees. Those are my two solutions. Is there any solution where sine is going to be negative between 0 and 180? No, because all values in that quadrant and all values in that quadrant are going to be positive. So looking at where the restriction is, looking at this part of the question and knowing where the angles are coming from or which values they want is also important. Or as I say, RTQ, right? Read the question. I think we'll leave this here for this moment and come back to the ideas of sine and cosine graphs and translations in the next video. Hopefully this has been of sense. We'll see you next time.